What's up, nerds? Harbinger here. We're doing the flip video today for one of my favorite topics in computer science. Today we are doing recursion. Now the problem with recursion is in order to understand recursion, you must first understand recursion. So before I show you the daily meme, let me set the table here. You've all seen in Algebra 2, the recursive definition. It's when something refers to itself, and that's what we're doing on this video today. We're doing a self-reference so we can do something over and over and over and over, and everything relies on static methods. So you have to make sure you're good on static methods. And before we do everything, let me just tell you, and I'm going to say this again later, there's two kinds of people who do recursion first. The first time you do recursion, you either struggle with it and it is a pain in the neck and it's not easy at all, and oh my gosh, you suffer, and you do it some more, and you do it some more, and you do it some more, and eventually it starts to make sense. Or you're the kind of person that looks it up online pretty quickly. You crow about how awesome you are at recursion, and you're secretly weeping inside. So I prefer like person A, but hey, if you need help on recursion, Coding Bat's got some good problems on recursion. Let's get rolling. So first, your meme for the day isn't really a meme. It's a nod to recursion. It's like Inception in a way. Like recursion is similar to reception. I hope I said Inception there, not reception. Recursion is a self-reference. Is when something asks itself for help. So we got like a 3D printer printing a 3D printer, printing a 3D printer, printing a 3D printer, etc. So this is good. It's not that dank, but you know, I like it nonetheless. So a couple things really fast. I'm going to illustrate some topics, and then we're going to talk about it. So just to give you a visual, this is a fractal tree. I wrote this in Java. I learned how to put sliders on there. I made a nice GUI. And what it does is, in terms of how Java works, it draws a tree, and by drawing a tree, it makes a line, and then it turns and may or may not draw a tree that's smaller on either side of it. So I've got this tree, and then it turned, and it said, well, I'm going to draw a tree over here. Oh, to draw a tree, I draw a straight line, and I turn and I draw a tree on either side of me. And each one of those says, oh, to draw a tree, well, I draw a straight line, and then I draw a tree on either side of me. So it looks like that. It's trees all the way down, pretty much. And this happens in nature all the time. You know, when you look at a tree, sometimes it's got like a big branch or something like that, and each branch has a mini branch coming off of it, which each of those is a mini branch coming off of that. And a lot of things in nature are fractals. So this is my first attempt at a GUI in Java making trees. It's kind of lousy, but kind of fun anyway. You know, I've never really put sliders on Java stuff before, and I changed the angle too. So maybe I wanted to make like a weird looking tree. You know, I don't even know, but I thought it was cool and it's fun to play with. So that's one example. Let's see. I did one in Python. Same kind of deal, although I think it looks a little bit more tree-like. You've got the brown branch, and then it backtracked a little bit, and coming off of that, it made a branch, which coming off of that made a branch, which coming off of that made a branch. And since you're a pro with ifs, I had it so if I got down to a certain branch size, sometimes I could leave a little leaf on the end. And if you want to know what that looks like, I made a forest. So each of them were different. Hey, draw a tree, and it went up, and it drew a branch on either end. And each of those drew a branch on either end, and each of those drew a branch on either end, all the way down until it got leaves, which I thought it looked kind of cool. This took about an hour and a half to render because my code isn't always efficient, and the school computers aren't always the best for rendering high-quality graphics in a really quick pace. But hey, I thought that was kind of cool. It's a neat illustration, and when you see it in movies, there's a lot of fractals and recursion going on in movies, typically in things like lava scenes. You know, like on Mustafar in episode 3, there's a lot of recursion going on in there in terms of the graphics. So you see a lot of recursion with graphics. And I know that you've seen recursion with graphics before because I know that you have seen our Google Classroom art. So I've got one recursion example, and I picked it for you guys. It's triangles right on the top. And each one of those says, hey, when you draw a triangle, find the midpoint of each side, and coming off of that, draw a triangle. Which, of course, the static method says, well, when you draw a triangle, find the midpoint of each side, and coming off the midpoint, draw another triangle. And coming off the side, draw another triangle. All the way down until we hit a certain stopping point, which is called the base case. So anyway, I thought that was a really cool example. The other cool example that I can think of graphically that you've seen before is the paint bucket fill in Paint. You know, you have a shape, and it's got some borders, and maybe I want to color this entire area blue. And you click the blue, you click the paint bucket fill, you click, and it fills that little area with blue paint. Well, that's recursive, right? It's a method that calls itself for help. And I called my method bucket, and it takes in 2 integers and a color object. And the integers represent kind of what pixel I'm on, and the color is what color I'm talking about. And it's got a couple, it's called base cases, which are stopping points. Otherwise, you get something horrible called infinite recursion. We haven't talked about it yet. But hey, if the color I'm on right now is black, stop. Because that's like the border between 2 colors, right? I had a black and white image, and I had black lines kind of demarcating little color areas. And if I want to, like, if you've ever seen a coloring book, you know, I want to color between the lines. Like, I want to color inside those areas. Otherwise, if I reach the edge of the image, stop. I don't want to color off the edge of the page. Otherwise, if I run into a color that I'm on right now, like if I'm coloring something red and the pixel I'm about to color is red, stop, because otherwise a red pixel is going to try to color its neighbor's red, or we're going to try to color it red, and it's called mutual infinite recursion, which again is a cool thing, but it's a horrible thing. So if it's black, stop. If it's the edge, stop. If it's the color I'm on, stop. Otherwise, well, draw a dot where you are. And then recursively call it again and again and again and again. So what that means is, hey, if you get a stopping point, stop. Otherwise, you paint where you are, and then I'm going to call this method all over again. This one is left, and this one's to the right, and this one is up, and this one is down, weirdly. But the method calls itself over and over and over and over and over until it reaches a stopping point. I know some of you right now are yelling like, why don't you use a loop? It's so much easier. We haven't done loops yet, right? We're pros at static methods, so I'm going to be using static methods to show my stuff. So I've got 2 little tiny brief videos for you. Whenever I think recursion, the body of the methods go like this. And I'm going to use this again in a second, maybe. Depends how good I am with the video. So The Grinch Stole Christmas is my absolute favorite cartoon, especially at Christmas time. He steals an entire town's Christmas. Having moved before, moving one house is crazy enough, but he moves everybody's stuff. He leaves crumbs much too small for other whose mouses. Dude, that's cold. But anyway, it's this scene in particular I'm drawing your attention to. So, there was a bunch of recursive calls in there, right? Each little who has a serving platter, and when he opens the serving platter, another who comes out with the serving platter. So the recursive call is the who is asking the other who for help, and a smaller who is asking a smaller who for help, and a smaller who is asking a smaller who for help, over and over and over and over and over, until they reach a stopping point, which is called the base case, and in this case, the stopping point yields the strawberry. And Cindy Lou Who is about to eat the strawberry. So that was 14 seconds of recursive awesomeness. And I'll leave that. So let's get into the actual Java code. That's you. I'm Ivan Drago. I must break you indeed. So let's get rolling here on recursion. Taylor, what do you think about that?
Are you ready for it?
No, they're not ready for it, but let's go anyway. So, recursive method. I'm going to do the one that we had as a challenge problem. And I know some of you were like, oh, I got it. I'm so good at it. I found it. Yeah, I know you found it. So I'm going to do what some of you worked hard, for the record, and I know that you worked hard, and I know this is a struggle, so I'm happy to see people doing really well. Let's call it factorial, right? I'm going to return an integer. I'm going to take in an integer. I can't call it int. Let's call it like input or something like that. So what we can't do is just like call itself over and over and over. Because really, factorial of 4, I know people are like, oh, it's 4 times 3 times 2 times 1. or it's 1 times 2 times 3 times 4, which is awesome. But really what it is, if you think about it, I'm not going to type factorial over and over and over. 4 factorial is really 4 times 3 factorial. Right? If you think about it, that's the recursive definition, which means your teacher's a jerk, but it's correct. And then 3 factorial, I don't know what 3 factorial is, but it's 3 times 2 factorial. And I don't know what 2 factorial is, but I do know that it's 2 times 1 factorial. And I don't know what 1 factorial is, but, oh wait, I do. It's 1. Right, that's called the base case. So I have these recursive calls up here, in which a factorial is kind of asking another factorial for help, and I have a stopping point. Hey, my stopping point is 1. So 1 factorial is 1, and it shouts back up here. It's like, hey, you're 1. And it's like, oh, okay, I got that. That means I'm 2 times 1. And that's 2. And it shouts back up to the previous method. It says, hey, 2 factorial is 2. So it's like, okay, I can do that. I'm 3 times 2, and that's 6. And then it yells back up to the method ahead of it, hey, I'm 3 factorial, and I'm 6. And it says, okay, well then I'm 4 times 6, and I'm 24. So really what it does, if you trace the actual code how it runs, it does the initial call, and it kind of gets interrupted because it doesn't know the value of that thing. And so it goes to compute the value of that thing, and it doesn't know the value of 2 factorial. And 2 factorial doesn't know its value, but it knows that it's 2 times 1 factorial, and it asks 1 factorial, and it's like, oh yeah, I'm 1. And then it goes back up through. So they're methods that kind of hit the pause button for a second, and it waits for a response back. Right? So every recursive method has 2 parts. It has a base case, which is a stopping point, and it has a recursive call, which is like asking a version of itself for help. Now, you got to keep your mind on the fact that you're working towards the stopping point every single time. Every time I ask, like, what's the simplest possible thing I could deal with? So, what's the simplest version of the problem? And so for us, it's going to be 1 factorial is 1. And then how to make a complex version a little simpler. So with this, I'm going to do it in pieces here. If input is 1, if I could type, stop, right? Return 1. Hey, I got this. What's 1 factorial? 1. Okay, what's 50 factorial? I don't know. What is 50 times 49 factorial? So how to make a complex version a little simpler? I could do that. I don't even need to type the word else, but I think some of you will anyway. I think it makes you more comfortable. Return the number I'm on times a simpler version. So factorial of input minus 1. Minus 10. So what you can't do is input minus minus, right? It's got to be input minus 1 because that moves me from 4 down to 3, down to 2, down to 1. But that's done. That's the recursive definition of factorial. Now, if I didn't have the base case, if I didn't have these 3 lines, it actually still runs, but you wouldn't have a stopping point. It would go 4 factorial down to 3, down to 2, down to 1, down to 0, down to -1, down to -2, and it would just keep going, right? So that's infinite recursion in theory. There's no stopping point. It just goes and it goes and it goes and it goes. It's kind of like an infinite loop if you know what loops are, but at this point, let's say no, we don't. So that's kind of a cool problem. And there's other ways too. So I'm going to do one with a string. And maybe I want to know how many of a certain letter there is in a string. So I would call it like write a method that takes in a string and a char. Why not? And count how many times the char appears in the string. So if I give it something like beekeeper and the letter E, it should look at the E in position 1, the E in position 2, then the 2 E's after the letter K, and then the last E, so it should return 5. So I'm going to do a recursive definition here. So public static, I'm going to give back an integer because I'm going to count something and give the information back, and we can call the method whatever we want. So public static int, I don't know, letter appear, I guess, whatever, string word, and char ch, I guess. So what's the simplest possible, what's the base case? And what's the easiest possible string there is to deal with? And that would be a string of length 0, right? So if word length equals 0, we're done. Return 0. You know, I can count how many times a certain letter shows up in a string that's empty. It happens 0 times. So that's not that horrible. And then how to make it simpler. So recursive case. What if it's not length 0? What if there's something there? What if it's a single character? What if it's 1,000 characters? I don't know. And to be honest, I really don't care because I'm going to work towards that. I'm pointing with my finger. I'm going to work towards having a length of 0. So I know a lot of you like the word else here. I don't need it, only because if I got down here, it means this didn't happen. But whatever, else works for me. I'm going to need a couple else's in the next problem anyway, so this is good practice. I need to know if the first, I guess I do need else. I need to know if the first character is the one I'm looking for. So word.char at 0 equals ch. Right? Hey, if that first letter in the word that I'm looking at is the one I'm looking for, great, I found one. 1 plus, oh my gosh. So I know some people are stopping right now going, wait. Why just char at 0? Well, that's because the only thing I know is the length is bigger than 0, right? It could have a length of 1. It could be 1 letter. It could be a length of 1,000,000. And all they have in common is there is at least 1 letter in it, which means I'm going to look at the very first letter, and maybe it's the one I'm looking for. I don't know if it has a second letter in it, or a third letter, or a billionth, whatever. All I know is I found one, so hey, I got one, return 1, plus, well, I gotta do LTRPR. I gotta do a shorter version of the string I'm looking at, right? I gotta chop it down. So how do I chop it down? Well, I'm gonna substring it. And I know that makes some people uncomfortable. Right? What this does, word.substring1 says pretty much I'm going to chop off the first letter. It means, hey, this is a substring of starting at position 1 and everything else after that. Remember, a substring, if it only has 1 argument, it starts at that letter and goes all the way to the end of the string. So that's what this one does. And I'm still going to look for that same character. I'm not going to mess with ch, right? That doesn't change. Else, so the first letter is what we're looking for. This is where comments really help. Else, so what if that very first letter isn't the character we're looking for? Well, this is going to sound dumb, but I always do 0 plus, and then I'm going to do the same exact thing. So I know some people are like, why would you add 0 to it, right? Why not just that? Yeah, you're right. But at the same time, this shows me like, hey, I didn't find it. So 0 here plus whatever you find smaller string. So I have an if, an else if, and an else. So my base case is if I had no letters, I clearly didn't find the letter I'm looking for. Otherwise, if that thing in the beginning is what I'm looking for, great, I've got one plus whatever they find after me. Otherwise, I didn't find it in the very first position, but keep looking after me and we'll see what happens. And eventually, word.substring1 is going to keep chopping off the first letter. You're going to keep looking at a smaller and smaller and smaller string until it reaches the length of 0, and it climbs back up through and counts appropriately. So that's actually a really cool feature if you think about it, right? It's like asking yourself for help over and over, and like it's like Cindy Lou Who there receiving the strawberry at the end. This is the strawberry at the end, and these guys right here are the Who's with the serving platters. So that's a pretty sick recursive method. I kind of wish I saved that one for the lab, just because, you know, I think it's pretty good. So the last but not least, we're going to do one we did previously in the year, except this time we're going to generalize it. On the conditional lab, you had to find out how many digits there are in an integer. and you had an if statement and an else if and an else if and an else if and an else, that's cool. But I'm going to make it a little bit different. So public static int, how many digits in a, let's call it a positive int. My thanks to those of you that do like num equals math.abs num, just to make sure that it's positive. That was really well done in some of your parts. That's cool. But for now, let's just pretend like it's a positive integer. This is called the precondition. So I'm only going to go under the assumption that whatever they feed me is a positive integer. So I'm going to call it like dig count. Right? I want to count the digits. And I'll call it input. It doesn't have to be. So what's the simplest possible number to count the digits? And you hear when people yell, 0! Yeah, because 0 has one digit, but at the same time, not just 0, there are other numbers that it's easy to count their digits as well. So I'm going to do that. That's the base case. A single digit number. Right? So if, how do you tell if something's a single digit number? If input is less than 10. Return 1. Hey, how many digits does the number 7 have? Well, it has one digit. Done. Otherwise, oh gosh, it's bigger than 10. Like, it's at least 10. So I've got 1 plus, let's chop it down a little bit. Oh gosh, how do I chop down an integer? Like, how do I turn 75 into, like, saying, oh, I got 1 because it's bigger than 10, plus, what's a smaller version of 75? Typically on recursion problems, you are asked to mod by 10 or divide by 10 because that chops things down, right? Modding by 10 would give you the ones digit, which I don't really want, but dividing by 10 chops the ones digit off. So something like 123, this would just be 12. And then 12 divided by 10 is 1. So dividing by 10 is a really effective technique in recursion with integers because it chops off the ones digit. It makes the number smaller every time. So this method is done. You know, like I could say something like down in public static void main string args. It could say something like SOP dig count of 5, 4, 3, 2, 1, and it would jump up here and it would say, well, this isn't true, but it's 1 plus dig count of 5, 4, 3, 2, and it would call this method all over again and say, well, 5, 4, 3, 2 isn't less than 10, so it's 1 plus dig count of 5, 4, 3, which is 1 plus dig count of 54, which is 1 plus dig count of 5, which is 1. And every single time it would go back up through the method calls and say, hey, we got this, there's 5 digits. If you really want to see something kind of cool but kind of weird, you can system that out.println inside the static method, and you could say, you know, input or something like that, just to watch the method work. But remember, on the AP exam, don't have side effects. You can't put system.out.println stuff inside methods. Just if you're tinkering around and you want to see it work, put it in there to see what happens. But anyway, that's recursion in a nutshell. And again, we got to be really careful because we need the base case. Otherwise, infinite recursion happens. Right? That's like your computer will just churn and churn and churn and churn and churn, and you either get a Stack Overflow error, which is how the site got its name. It's like the main error that people have when they're doing recursion, or your computer just churns at it for like an hour and then crashes. Neither one is fun, so the base case is important. Otherwise, you're always asking yourself, how do I work towards a simpler case every single time, and what's my stopping point? All right, so if you were to Google, oh my gosh, I can't remember the last time I typed in Google. You can Google recursion, and it says, did you mean recursion? So even Google has an Easter egg about recursion. Be careful. Think to yourself every time, how can I make this simpler? What's the simplest possible stopping point? And we're going to have a lab on this. We're going to have some paper homework on this one because recursion is not going away. It's on the AP exam a lot. It's in college a whole lot more than it is in high school. So we got to make sure you're good for it. And I hope you're all enjoying your weekend. Harbinger.